welcome back. This is the continuation of the previous lecture. In this lecture, we are going to talk about gate drive circuit in this training kit, current sensing circuit, as well as some schematic guideline for this training kit. So, this is the complete test setup and which is used in our course, and I will be showing multiple demonstration, experimental demonstration case study. This is a power stage, and we have already demonstrated the mixed signal conditioning circuit. So, now here the basics of CMOS gate drive. So, before we go through the gate drive circuit, we first understand that if we consider a MOSFET, that means if you are talking about a MOSFET, this is the drain, source, and this is a gate. So, in order to turn on, turn off any MOSFET, right? So, we need to provide sufficient, that means it require a buffer circuit. What is the buffer circuit? That means this buffer circuit is nothing but back to back inverter, CMOS inverter. This is a very basic of gate drive. And what does it do? So, if we take a CMOS inverter, I think we have discussed in the earlier lecture. So, it is nothing but very simple circuit. So, this is our, let us say, gate signal Q, and this is the inverter. Then we want to connect the other inverter. That means, what we want to show that this is the first inverter, this one represents one inverter, then followed by this there will be another inverter. Now, I am drawing a bigger scale. So, this is VDD and this is going to your actual gate. This is actually going to the gate. That means, this is nothing but this terminal. So, what does it do? This is also another inverter, but the size of, that means the W by L ratio is much higher. That means, why? Because the MOSFET requires certain amount of gate charge to turn on. That means, we need to make charge, we need to fast charge, right? Because if you take the MOSFET very fast characteristic, there is a capacitor. So, we need to charge the gate capacitor, because the gate will have a capacitance. So, we need to charge the capacitor. Since the capacitor is large, depending upon, suppose if you consider the figure of merit of the MOSFET, which is the product of RDS on into QG, that is a gate charge. So, if the RDS on is small, typically QG is large. That means, if you are trying to reduce the conduction loss, your switching loss increases because QG large, and if the QG is large, that means the gate capacitance is large. So, you need a faster charge rate. That means, the driver current requirement is very high. That means, you need, this is the gate current has to be sufficiently high to fast charge and discharge the gate capacitance. So, this is I am talking about the CGS, gate capacitance. So, the gate capacitance has to be charged very fast in order to turn on and turn off this device. That means, you need to provide sufficient current, and that is why this path should carry much more current and W by L should be very high. So, the basic of the gate drive, it is a two stage, like a two back to back inverter. The last stage inverter consists of a larger sized the CMOS transistor, which can carry high current in order to fast charge and discharge the gate capacitance of this MOSFET. That is the basic starting point of the gate drive. So, that means the gate drive, because it is a CMOS technology, the first will invert and then finally invert. So, naturally this process of back to back will also have some propagation delay. That means, if you see the actual gate signal Q, and here whatever is coming out to QG, there will be slight delay because of this back to back transistor, back to back inverter. But we can understand that this CMOS transistor is responsible for charging and discharging the gate capacitance of the MOSFET, and if the QG of the MOSFET is high, then the peak current rating of this driver circuit has to be large, high, in order to fast turn on turn off this MOSFET. Now, when you go to half bridge gate drive, so this is one product from ST Microelectronics. So, these are the power stage, this will get connected. So, I will just connect to the power stage. So, that means this is a complete picture here. This is a high side half bridge switch, the high side switch, high side MOSFET. It can be MOSFET or any other devices, and this is our low side MOSFET. That means, if you are talking about a synchronous buck converter, from here we generally connect the inductor, right, for the synchronous buck. But here this is a driver, so we need to turn on and turn off this high side and low side gate drive. So, that means, the job of this particular device in the previous, this is a back to back transistor that I told, that will turn on turn off. This is a back to back transistor. Okay. Now, for the low side, the ground is the reference. So, it is easy. So, we can create the gate drive voltage and you can turn on turn off. But what will happen the high side, where the source of this MOSFET is floating. So, that means, you need to do some kind of there are two ways, either you can create, that means the gate drive voltage, that means I am saying that you have a MOSFET which is like this is a high side MOSFET, where the source is floating, it is floating, the source voltage can vary based on the switching condition, and this side can be input voltage or something else. So, now I want to create a driver. So, the driver, what will be the driver ground? So, the driver ground should be connected here. Now, then a driver also need a supply VDD. So, the driver supply should be such that the VDD should be Vs, that is this voltage, plus your, I would say, the required voltage to turn on and turn off the MOSFET. So, this is the voltage. In case of low side, this is 0. So, let us say the MOSFET gate voltage is 12 volt, 10 volt. So, this will be the 10 and 12 volt, but this is source voltage. So, you have to create a voltage here which will be which will add this voltage over the source voltage which is floating. So, how to achieve that? So, this is a gate drive circuit. Okay. That means, this driver, how to do that? So, one way is that we can use a bootstrap arrangement, because this is a bootstrap capacitor. So, this capacitor will be charged to that required voltage, that means, this will actually create the required voltage, this will add up with this source voltage and it will finally generate create the VDD. So, your VDD for the high side, gate drive will be V source plus V required, and this required voltage will be stored, I mean it will be created by the bootstrap. So, this bootstrap capacitor is responsible to create that additional voltage, required voltage for turn on and turn off. So, this capacitor, if it should be somewhat large. At the same time, you should provide certain on and off time to balance the charge and discharge. Otherwise, if your off time is too small, or if you turn off the switch continuously, if you turn on this switch continuously, that means in a buck converter we have this high side switch and the low side switch. We have this high side switch and the low side switch. This is the inductor. Now, suppose we want to achieve, let us say 95% duty ratio. Duty ratio is 95. That means, if you are operating a switching period of 1 megahertz, that means your T is 1 microsecond, then what will be your on time? if it is 95% duty ratio, so it will get only 50 nanosecond. Sorry, 99%, so off time, this is the off time, And what is your on time? T on, so T on will be 950 nanosecond. Now, during T on, this capacitor has to supply to this gate. That means, this will be charging the capacitor of the MOSFET, the gate to source capacitance. As a result, this boost trap capacitor discharge. So, if the boost trap capacitor is not too large, then it will actually discharge and it cannot provide sufficient voltage and the MOSFET can turn off. But if you put a too large boost trap capacitor, then the time constant can be large and that can create another problem. So, that is why in majority of the current commercial product, they put a constant in terms of duty ratio limit. That means, you may not reach 95%, some product may go like 80% or so. It all depends on what is your time period and what is the absolute, I would say, on time or absolute off time. So, those will decide the boost trap capacitor design. But in summary, I would say the high side circuit we may require a boost trap capacitor to solve. But there is another approach. We may not need a boost trap if we can generate the driver supply through an isolated power supply. That means, here the driver and everything is generated from the common ground, which is same as the power ground. But if we can create an isolation with the supply of the driver and the supply of the power stage, then we can easily connect this here of the driver ground, which is an isolated ground, can be connected to the source, and then we have to simply generate the additional voltage here. So, that also require isolation. That means, the type of gate drive can be non-isolated, which is a boost trap, high side, low side, half bridge. We have discussed half bridge. Low side is much simpler. This is just a back to back. The simplest one is the back to back inverter we have discussed, and the high side we may need a boost trap arrangement, and half bridge we have discussed. Isolated, how do we isolate? So, that means there are isolation can be optical isolation, but this will also have a limit in terms of switching frequency, because it cannot be so fast turn on turn off may not be possible because of the bandwidth limit. Similarly, if you go for a magnetic isolation by means of flux, so it can use a high frequency transformer, it still has a limit in terms of switching frequency. Now, people are going for capacitive isolation, which can be faster, and like a digital isolator. Suppose if you want to because this is for isolated converter, suppose you have a gate signal, let us say you have generated gate signal Q, but this gate signal with respect to some ground 1, but you want to generate a gate signal dash which will be same, but it is with respect to some ground 2. Then what will do? Between Q you need a digital isolator and Q dash. So, this is something like a digital isolator. So, this can be a capacitive isolator which can be much faster, which can support tens of megahertz switching frequency even far. So, these are the challenges now coming when you are going for half bridge gate drive for gallium nitride devices as well as silicon carbide high frequency, where you may not simply go for a traditional isolated device. So, how to deal with gate drive, and there are many research as well as the commercial products are coming up. So, the gate drive boost trap arrangement we have discussed. So, the boost trap has to supply to this gate. So, we need to make sure that sufficient on off time is maintained and the time constant should be. So, we have to decide the on time of this switch and the time constant, there should be some kind of balance, otherwise it may discharge. So, in this training kit we have used half bridge gate drive with boost trap arrangement. Now, the current sensor. So, here we have used a shunt inductor, that means inductor with a resistive sensor. So, we have used a resistive sensor, but when you want to sense this, we have to step it down depending upon what is the voltage level. And if you do that, then there can be some parasitic inductive effect because of this. So, we need to put a compensation in the capacitor. So, this is a compensation network, and these two will go to the two differential arrangement. This is a differential amplifier, and it will convert into the single ended voltage. So, that means we are getting a voltage which is Rg is this by R1 mean into the shunt resistor that we are using. So, that means we need a compensation in the capacitor in order to, because what we will see, if this is your actual inductor current, then you may find that the sense inductor current will have some kind of noisy stub, switch node stub. So, to reduce this effect, we need to put this capacitive network, but if you put a large capacitor, there can be phase lag. So, you have to be very careful about this selection. So, in this training kit, we have used this resistive sensing with the capacitive compensation and a differential amplifier. So, for voltage sensing also, we have used with respect to the power ground a differential arrangement, and that converted into single ended. So, here that means we have used the actual output voltage and we have tried to match. So, this is to reduce the common mode noise. So, eliminate the switching noise at the output, because we need to also try to avoid and try to reduce the noise effect. So, the power stage schematic, here this is the input side bank of capacitor. Then we have, so this is the input stage. Then after the input, because we are talking about the buck converter, this is a half bridge MOSFET that we have used. Then the MOSFET gate drive circuit is used here, the boost trap arrangement, all these things we have used here. And after the high bit gate drive, we have put a gate resistance. That means we have this gate drive circuit, this is like a buffer circuit we have discussed. Then we put a resistance, gate resistance, and this goes to the actual MOSFET which has this kind of arrangement. Okay. So, this is a gate resistance for both the MOSFET. So, that means this is a half bridge boost trap gate drive we have used. Then after this half bridge, now this is a tapping point, that means we need to put a wire, that means we have created a loop. And if we go back to our teaching kit, that means let us go back, we want to show that this is the loop we are talking about, this is a loop. That means if we take a different color, so we are talking about this particular loop, so that we can tap the current probe here. So, for that we have made an arrangement here, and there we can connect this wire, so that we can connect our current probe. This is inductor and this is a sense resistor, the shunt that we have discussed for the current sensing, and this is the output side capacitor. Next, the current sensing circuit we have discussed. So, we have used the current sense resistance, and then we have used this differential arrangement, and that will convert into single ended, and you can get the voltage. So, all this detailed pin configuration, all the values are given. So, one can make out about and get some guideline about the schematic. So, we have arranged the onboard load, that means these are the load that we have arranged which can be placed in parallel, and we have also, this is a switch, through a switch, that means this load can be connected or disconnected if you want. That means we have some continuous resistance, let us say this is the capacitor of the buck converter, this is the inductor, and we have kept another resistance with switch. That means if you turn on this switch, these two resistance will come in parallel, and then effective resistance will be reduced. So, it will make a load step up transient, and if you remove it, it will create a load step down transient. So, voltage sensing, this is the voltage sensing circuit we have discussed, that it is a differential amplifier is used, and that try to reduce the noise. And voltage reference generation, this is used for, because we have to supply voltages for different blocks, let us say. So, this like LDO based arrangement can be made. Suppose we want to supply for the current sensor, current sense amplifier, we want to supply for the driver. So, all these things, that means we have to generate the bias voltage generation. So, in summary, we have discussed gate drive circuit in this training kit, we have discussed current sensing circuit, and then we have discussed schematic guideline for this training kit. So, we have discussed somewhat detail about our teaching kit, and but again this experimental development and hardware prototyping is not mandatory for part of this course. One can use their existing teaching kit, but in the subsequent lecture we will show how to implement digital control using FPGA various steps. So, it is more important to understand the algorithm, basic concept of different architecture. That is it for today. Thank you very much.